In this demo, we're going to be looking at the chemistry that takes place inside of a light stick or glow stick, something you've probably seen many times. You take the plastic tube, crack a small glass capsule inside to release some chemicals, and then the stick starts to glow. The chemistry taking place inside of these light sticks is really interesting. It consists of a molecule called Cyalume, shown here in this diagram on the left, which reacts with hydrogen peroxide. When it reacts with hydrogen peroxide, it actually splits that molecule, which is symmetric, into two products. As an intermediate, it forms this square molecule, 1,2-dioxetane-dione, which then reacts with a colorizer molecule that is added into the mixture, which is excited and then emits light, producing the glow that you see. This reaction is a great way to demonstrate the temperature dependence of kinetics. Maybe at some point in the past you've had a light stick and stuck it in a freezer to preserve it for longer. In fact, you can keep it for about 6 months in a freezer after cracking it. Here, we're going to add heat to the reaction to see how it increases the kinetics of the reaction. On the left, I have a light stick that is just going to run at room temperature. And on the right, I've cracked a second glow stick, which I cut open and pour into this test tube here, which we'll use as our experimental. To show the effect of temperature, we dim the lights, and then I increase the temperature of the test tube on the right using a blowtorch. We can see pretty much immediately that as the test tube gets hotter, the reaction runs faster, emitting more light. Here we're zoomed in on the test tube, and I'm going to heat it up a little bit more to drive the reaction all the way to the end. As all of the Cyalume molecules are consumed, the reaction stops glowing, leaving just a reddish-orange solution. Comparing the two, we see that the light stick at room temperature is still glowing and will persist for several hours. To explain what we've observed here, we can consider the Arrhenius equation. By increasing the temperature of the solution, we've increased the average energy of each molecule, as well as increasing the frequency of collisions. Both of these contribute to a higher rate constant and faster reaction.